Welcome to the 7th Annual Climate Change Forum. The Pasadena League of Women Voters and 9 co-sponsors are proud to present this year's topic, which is what will happen when global temperatures rise, new scientific insights. My name is George Null, and I'm the Pasadena League of Women Voters Climate Change Forum Coordinator. I'm also doing all of the opening remarks. Dorothy Keene, the league president, has another commitment at the county convention in LA, and so I'll doing what she would normally be doing on the announcements. I'm happy to welcome you to the forum. Now is the appropriate time to thank those who have worked to conduct this event. We thank the following 9 co-sponsors for publicizing the forum and encouraging their members to attend. And the co-sponsors are Arroyo Seco Foundation, Climate Change Lobby, Climate Resolve, Eden, which is the All Saints Environmental Ministry, Interfaith Power and Light, Neighborhood Unitarian Church Green Council, First Methodist Church Risk-Taking Mission, Sierra Club Pasadena Chapter, and Transitions Pasadena. Now, several of those organizations have table displays today, and they would be, I'm sure, happy to sign you up if you want to join their organization, and they're happy to inform you about what they're doing. If you'd like to join the League of Women Voters, there's materials back there for that as well. The First Methodist Church provided the fellowship hall, which is the venue here, for the forum and much other valuable support. We particularly thank Maggie Audley, the church secretary, Deb Shepard, our risk-taking mission contact, and Sandy Olewine, the pastor who helped us get the audio working for today's program, and Frederick, who helped set up, who's from Kenya, who helped set up the facility. At this time, we would like anyone who's associated with forum co-sponsors from all those organizations and the members, their families, and their friends to please stand and be recognized. So if you're associated with any co-sponsor, please stand. Most of the forum preparations were performed by the Pasadena League of Women Voters Natural Resources Committee. Would the committee please stand and be recognized? If you're a committee member. Any other League of Women Voters members who are here, would you stand and be recognized? There are a lot. Thank you. At this time, I'd like to introduce Catherine Del Rosario, who's the district director for Chris Holden. Would you stand and be recognized, please? As far as the program, I don't know if you can read the agenda that we have here, but there will be a Q&A after each speaker will speak 45 minutes. There will be a Q&A after each speech, so please hold your questions until the Q&A. The Q&A will be the same way we did it in previous years. Questioners will line up in the center aisle, and when it's your turn to ask a question, this year we're going to have you come up and use this microphone so that we can hear you without having to repeat your question. And then the speaker will answer. The speakers will be controlling the Q&A. I'm there to jump in if there's a problem. The thing about questions is that it's okay to frame your question, but please don't make a speech, okay? We're very fortunate in the Pasadena area to have 2 very outstanding scientific institutions, Caltech and JPL. Many of us are associated with one or the other of those. Rhodey Stevenson, who was our chair 2 years ago, was a lifetime JPL employee, and so was I in the engineering side. The speakers today, both of them are from JPL. They're climate scientists. So we're very happy to have them make these presentations today. The first speaker will be Annmarie Eldering of the JPL lab, is currently the Deputy Project Scientist at the Orbiting Carbon Observatory OCO2, which is a satellite to measure carbon dioxide that was launched into space on July 2nd, 2014. She is also the project scientist for OCO3, a similar carbon dioxide instrument that is planned for installation on the International Space Station in February 2019. The smog of Los Angeles enticed her to come to Pasadena 30 years ago. I did a double take when I read that too. And she studied air pollution during a PhD at Caltech. She has been at JPL for 20 years, starting as a research scientist, doing detailed modeling of how light moves through the atmosphere when there are clouds and pollution, and what that means for satellite measurements. At JPL, she has held a number of leadership and management positions and joined the OCO2 project in 2010. Annmarie?
So thank you very much for inviting me to join you today. I'm excited to share some information about what we're working on and some of our newest scientific findings. I'll try to be clear in what I'm telling you. If you cannot understand me, maybe give me a hand, and we'll leave plenty of time at the end for questions. All right, so we're going to talk about carbon dioxide and some exciting stuff we're doing from space. I'm here speaking to you today, but if my team came along with me, it'd be about as many people as we have here in the room. We're big group projects up at JPL. These are complicated instruments to build and data sets to work with, so it's always a team activity. So you're just seeing me as the front, but there's a lot of folks that are involved to make this happen. And here we go. So I'm going to start off talking a little bit about what greenhouse gases are, where they are in the atmosphere. My apologies if this is all familiar information to you, but just get you warmed up on the topic. And then I'll talk about some of the big questions we have scientifically, what's happening in our world, what we understand, what we don't understand, and then we'll talk about what we're doing with the satellites to help answer these questions. So greenhouse gases, if you've sat inside your car on a sunny day, you know how it can get very warm because the sun's shining through the windows, but the energy that's trapped can't escape back out the windows. And that's similar to what you do with a actual greenhouse. If you want to garden in the winter, you might build a glass house because it can trap the energy. Sunlight shines in, it turns into heat that doesn't go back out. And this same phenomena happens in our atmosphere. The atmosphere around Earth serves as kind of a blanketing mechanism. It lets energy come in from the sun, but it traps a certain amount of the energy, keeps it from going out. And that's really important. If we didn't have that blanket of the atmosphere, the Earth would be really cold. It wouldn't be a good place for you and I to live. But this blanketing of the atmosphere has kept us at a nice temperature that's been pretty good for plants and for humans and for the things we're doing on Earth. So we have these greenhouse gases that naturally occurring in the atmosphere. But what we also know is if we put more greenhouse gases, we'll get more blanketing. So
Really close to this, kind of like that, so
okay.
that you can pick up one of this.
So if we put more of this blanketing gases in the atmosphere, we'll get more trapping of the energy. And so this is just a figure that's showing you since 1880 till about 2010, the red and then yellow lines are our best estimate of how much carbon dioxide, a greenhouse gas we'll talk about in a moment, how much of that gas was present. And you can see it was going up over that time period. And then the blue line is the temperature record in that same period. And it doesn't move smoothly, but over time it is moving up. So we have evidence of increased temperatures, and through a lot of fundamental physics, as well as these kind of relationships, we can see the tie between the greenhouse gases and the temperatures. Sorry. So greenhouse gases, I'm going to talk about carbon dioxide. So CO2 is our scientific nickname for carbon dioxide, and I'll use those two things interchangeably, CO2, carbon dioxide. It's a very important greenhouse gas produced by humans. And methane is another one that comes from agriculture. It comes from when we remove gas, do oil extraction, we can release methane. And there's others like hydrofluorocarbons. You know that your air conditioners have changed over the last 20, 30 years because we recognize that these gases contribute to greenhouse warming. And this figure just gives you some sense that carbon dioxide is the biggest human-produced greenhouse gas. Methane's significant, and then these other ones are smaller slices. So I'm going to focus on CO2, carbon dioxide today, but there's others that are playing a role. And where is this carbon dioxide? It's not a gas you think about. It doesn't smell, it doesn't have color, but it's actually all over the place. It's in the atmosphere. When we breathe in and then breathe out, we're expelling carbon dioxide. When we have plants in our environment, they'll remove carbon dioxide in the process of growing, and they release it when their leaves die and rot. It's dissolved in the ocean. You know that when you open a can of soda, it's bubbly and fizzy, and that's actually dissolved carbon dioxide. The gas dissolves in liquids and get released. How much dissolves changes with temperature. So this is all over the place, carbon dioxide. And what I'm going to talk about is actually this exchange between atmosphere, ocean, and land, and how that's what's happening, how it's changing, what we understand and what we don't understand. So this is a photo of scientist Charles Keeling. He was a really important guy in the world of greenhouse gases, and just down here in San Diego, not far from us. And back in 1958, he had the insight to think about how carbon dioxide might be changing because of human activities, and he wanted to have a deep understanding of how much there was and how it was moving around. So he established a measurement on Mauna Loa over in Hawaii that's become one of our most critical records of long-term carbon dioxide. So this is Charles Keeling. This is a washed out map of Hawaii showing you where that measurement is. And you can go take a tour of Mauna Loa, drive up to the top of the volcano where this station is. So this is an important step that happened in 1958. And now I'm going to take a numbers break. So I don't know if y'all are numbers people. Ian and I are certainly numbers people. So one number I want you to remember when you go home today is the number 400. And 400 parts per million is roughly our current concentration of atmospheric carbon dioxide. So us scientists, we think of a lot of crazy units to use. Parts per million is one of those. So here's a few ways you might remember it. If you take the area of this green box and compare the red box is 400 parts per million of that green. So that fraction of color is the proportion to the green of 400 parts per million. Another way to think about it, let's say you hit the lottery and you had $1 million, and 400 of those were colored pink. That would be 400 parts per million. Maybe more realistic, I have $2,500 and one of them is pink. That's 400 parts per million of my dollars. So that's our current concentration. And one of the things is it's a small amount, but not infinitesimally small. And we use parts per million so you don't have to have a lot of leading zeros or trailing zeros, but 400 parts per million. So I mentioned Charles Keeling had the insight in '58 to think, we really should start measuring carbon dioxide and take a record of how much there is. So this is a graph that's showing you since he started that record in '58 up till when I downloaded this last week. There's a time series. So in Hawaii, these are measurements of carbon dioxide taken over that time period. So there's probably two things you can quickly understand about this time series. One is that from the start of his record till today, we've seen a change from a little under 320 parts per million to over 400 parts per million. So you can see in that time period of this record, we've increased about 25% the concentration of carbon dioxide in the atmosphere. And then you also notice there's a red line and a black line. The black line is kind of the smooth time series. The red line is the actual measurement data. So it shows this kind of seesaw behavior in it. And I want to take a minute to tell you why that's happening. So this is just saying we can break down this curve, this measurement of carbon dioxide over time, into two pieces, where one is this up and down feature and the other is an increase in time. And so why is that up and down happening? Well, it's really driven by the natural environment and really the trees and the plants in the world around us. So in the springtime, when trees start growing, they're actually taking carbon dioxide out of the atmosphere to make their leaves and their plant material. So if you had, let's say you had that 400 parts per million, the trees want to take some of it out, it's going to start to drop down. By the time I get to the summer, that plant growth is really happening. It's taken out a whole bunch of carbon dioxide, and we're down near the bottom of that curve. In the fall, the tree growth is stopping, leaves are starting to fall off, so you don't have a drawdown anymore. And then by winter, those leaves are rotting probably. They basically fall apart and release that carbon dioxide back up into the atmosphere. So a way you can think about this up and down that's happening with season is you start with spring and summer, and the plant activity removes carbon dioxide, turns off in the fall, and then the rotting puts it back up in the atmosphere. So we get this cycling up and down that just happens because of the trees and the plants and their natural cycling. So what about this going up in time? So I think a good analogy for going up in time might be our bank, hopefully our bank accounts are a good analogy. So if you think about running your house, you have a certain amount of money that comes into your bank account, you have a certain number of bills you pay, you at minimum probably hope to have some balance between those two things, right? The money comes in equals the money going out. Maybe you're in a situation that the bills you pay are less than the money you get in. And so over time, you're going to accumulate more and more money in your bank account. So our atmosphere is a similar situation. You've got some carbon dioxide going in, and we'll talk about that more in a moment, but we burn gas and oil and coal, and that puts carbon dioxide in the atmosphere. We have ways that carbon dioxide goes out, like it goes out through plants and dissolving in the ocean. But the animals and the plants also can put it back in. So the question is, are these all in balance, or is one of them dominating? Do we have more going in the system than going out? And in fact, we have more going in than we have going out, and that's why it goes up and up and up over time. So the net increase in time is just because there's more carbon dioxide getting in than I have a way to get out. And burning oil and coal and gas is really that big driver of increase over time. The natural system, the ocean tends to be somewhat balanced. What it releases is about what it takes in. And we talked about the plants that grow and then they die, and they grow and they die. So they're kind of balanced over time. This is just showing you a graph again since 1958 of how much carbon dioxide is put in the atmosphere through different activities like burning coal, burning oil, burning natural gas, and making cement. And the main point I want you to get is that these curves are continuing on an upward increase, and that's the driver of this increase in concentrations over time. So if we kind of make a balance sheet again, back to our analogy of your bank account, what goes in and what goes out. So this is what's going in, the sources. 91% of what we add each year is from burning of fossil fuels. And then actually, if you cut down more trees than you let grow, that net puts carbon dioxide in the atmosphere, and that's about 9%. So these are places carbon dioxide is coming from. And then we use the word sink to talk about the way it's removed. And rough numbers, about half of what we put in the system stays in the atmosphere. About a quarter of it goes into extra trees, and a quarter of it goes into the ocean. So the ocean can dissolve carbon dioxide, and it's taking up more and more carbon dioxide over time. And these are really critical because they're really helping us out. If the ocean and the land didn't take that extra carbon dioxide, the rate of increase in the atmosphere would be twice as fast as it is. So you can think about the atmosphere gets about half of what the humans did, but the land and ocean take up about half and kind of slow down that process of increase. All right, so hopefully I haven't lost you yet. You remember your 400 parts per million, and then we're going to talk a little bit about this land-ocean atmosphere interaction now. So this is a rough number picture, and this is kind of an aggregated. I'm not talking about what happened this year compared to last. It's just on average, half to the atmosphere, quarter to the land, quarter to the oceans. So let's dive into a few details since I didn't lose you yet. So what's happening over time? So this is a graph showing, again, gigatons of carbon from 2000 to 2017. And the black line is showing the overall increases over time. And this much of it in the atmosphere, about half, and the rest in the ocean and the land. And what I want to call your attention to is the jaggedness of this line. And this is showing that every year is a little bit different. How much the land and the ocean can take out changes every year. I don't have it on this graph, but I'm going to give you this fact that the atmosphere number goes up. Back in the 50s and the 60s, we were seeing about 1 part per million increase each year. So remember Keeling's curve, it increased about 100 part per million since 58. In those early decades, the rate was just about 1 part per million per year. In the last decade, we're seeing numbers more like 2 or 3 part per million per year increase. So faster rates of increase, and that's because our rate of burning coal and gas and oil is increased as well. So we have changing rates over time, but this variability is one of the puzzles that I want to spend a little more time talking about. And another way to look at this is a longer time series. This is again paired up to Keeling. So over time, this much carbon dioxide is going in the atmosphere, being released. And in this one, we've turned it around. So the blue curves are what stayed in the atmosphere. The red curves are what the land and ocean took. But you basically see it's moving all over the place. So sometimes, I told you, on average, we have 50% to the atmosphere, 25 to land, 20 to ocean. But there's years where 20% of what we put up stays in the atmosphere, not a whole lot. There's years where 80% of what we added stays in the atmosphere. And we don't know exactly why it changes so much every year, and that's a puzzle we want to solve. The other puzzle is what's going to happen in the future. I want to understand this change from year to year so I can more accurately tell you what's going to happen in another 80 years. And the other thing, let me see, I think I actually wrote these questions down, is I'm talking about global numbers here. I told you on average this much is removed, but what we really kind of want to know is what's going to happen in North America, what's going to happen in Europe, what's going to happen in Africa, because their responses are important for their own policy planning, for what they think is going to happen to agriculture, for how they think it's going to influence their forest, etc. So we need to know this not just on an average across the globe, but each region. And this is what I was saying, it's important to know because you want to predict the future. This is a prediction out to 2100, and it's showing you that people kind of agree that the oceans have been taking up carbon dioxide and they'll probably keep going that way. People do not agree about the plants. So we've had more carbon dioxide in the land, and some people think that'll flatten out. Some people think it'll keep going, and somebody even thinks it's going to kind of turn around. And so that's a really important question. You have to know what's going to happen out here. And again, because land and ocean kind of soften the blow of what we put in the atmosphere. If the land stopped absorbing carbon dioxide, that rate of increase is going to be even faster. So that's some of the big questions. How is this going to play out over time? How is it going to play out over region? And sorry this map doesn't project that well, but I'll tell you with words what I was trying to show here is for many decades we had a number of scientific stations across the globe to measure carbon dioxide. We talked about Keeling. In Hawaii, there's stations around the globe, but they're total in these blue arrows are the key stations, and then there's some other measurements made with the red dots. There was about 100 places around the globe we would get this idea of how much carbon dioxide there was. And when I asked those questions about the future and how will things evolve, well, if you wanted to predict what was going to happen in the ocean here, you don't have a lot of information to work on. There's just one measurement station. Or in the land up here in the north, there's not that much information. So the data we were collecting wasn't enough to really help us answer this question on a regional scale. So those of us who work up at the Jet Propulsion Lab love to put things in space, and so some of the guys said, hey, we should put up a satellite. We need to get closer to the mic.
I'll just turn this a little bit.
Okay. So a satellite is a great way to go if you want to measure something all around the globe. If you want to see all corners of the world and see them every day, it's a great technique to use. So this is the artist rendition of the satellite that we put up. This thing is like kind of a telephone booth size with those 2 solar panel wings out on it. It's not enormous, but it only does the one thing, measure carbon dioxide. And just to briefly explain how we do this, we need sunlight to go through the atmosphere, bounce off the Earth, and come back to our satellite. And we look at this light at 3 different wavelengths. One of them is like what your eye sees. And if there's a cloud in the way, you know you can't see through a cloud with your eye. Well, our instrument doesn't see through the clouds. And these things that sort of look like barcodes are basically showing you that light of different wavelengths is removed or not removed in different ways. So when you see a cloud, this pattern changes a lot, and we can tell that real easily. Carbon dioxide also interacts with light in a very specific way, and these are 2 bands that respond to carbon dioxide. And so basically the lights change a little bit depending on how much CO2 there is, and we can tell that with the wavelengths we measure. And we have a lot of work to go on to make that estimate properly. Basically, we model how much light there should be. We say, well, let's say there was 400 parts per million. This is what the light should have looked like. If it doesn't match what we saw, we make a little adjustment, and we say, well, maybe there was 398. Model the light. Does it look like what we saw? And eventually, we can get an answer and know how much carbon dioxide there was. We also want to tie ourselves to things like Keeling's measurements. So we actually have measurements on the ground. This is an example of a special measurement that's made at the ground. We have one of these at Caltech. Aircraft fly over those measurements, and they use the exact same technique that Keeling used. So we kind of link the ground base to the aircraft, and they link the satellite to the ground base and tie it all together. I'm going to go straight to my little movie here. There we go. So this is a movie showing you some of the actual data we collected over the last 4 years. And the blue colors are concentrations around 390 parts per million. The red colors are 415. And over the course of a day, we see reflected sunlight about 1 million times. And there's a lot of clouds out in the world, but we get about 100,000 good measurements of carbon dioxide. So I told you there's 100 ground stations, and now we have 100,000 measurements per day. So much denser data set. And you can see there's data being drawn out across the whole globe because we're flying around with a satellite, we see the whole globe. And you can see there's patterns that are showing up like the blue, and this is where the plants are turning on and drawing that carbon dioxide out. You really see springtime and summer arrival very dramatically in this data set. And then we're here now in September, and then we'll start to get in the winter, and you're gonna see that northern hemisphere get much redder. And that's because most of the humans of the world live in the north. Most of the gas and coal and oil burning happens in the north, so when the plants are quiet and we're still heating our houses, we add a lot of carbon dioxide up to the atmosphere, and it increases concentrations, so especially in the northern hemisphere. And then we're going through another cycle here. This is now May, and then you'll see summertime hit in that northern hemisphere, especially over Eurasia. You see it suddenly got blue because the plants turned on and really draw that carbon dioxide out. And let's get to one more winter time here. So now we're in September, it's still pretty low, and now November, and you start to see it soften back up again. And once we hit this last December, you should see things kind of go in red. And there we go. And one of the tricks is trying to get a color scale so you can see both the seasonal patterns and this increase over time. There's a lot of stuff to see in the data, and you can't see it all in the one little movie I made. So we have tons of data now, so let me just touch on some of the science that we've been doing with it. So most of you are probably familiar with El Nino. We think about El Nino, are we going to have a rainy winter, are we going to have good ski season, or what's going to happen in California? Well, we also think about El Nino because it's a big global pattern. And this is just a little illustration showing you how in a normal condition, you have this cycle of movement of air in the atmosphere and winds over the ocean, that the winds in the equator tend to go from the east to the west, and the warm temperatures, water, stay over here. In El Nino, those winds have softened up, and now you start to get warm ocean water coming all the way over to South America and not much happening with the winds. And why do I care about that? Well, another effect is the cold water in the ocean follows this pattern in a normal year where it's rising up over South America. In an El Nino year, when those winds have changed, it actually kind of caps that water from upwelling. So you change the patterns of the deep water, and that's actually carbon dioxide rich water. So if these winds are changing and the water's not coming to the surface, we expect less carbon dioxide. And in fact, we saw that with our instrument, which was astounding to us. So in that big El Nino, 2015, 2016, this is just an index that tells you, do I have an El Nino or not? So this pink line is saying, yes, in early 2015, El Nino started happening. And this is a record of carbon dioxide near the equator from our data. And what you see right here is there's a drop in carbon dioxide. So we could see the ocean changing what it did because of El Nino, and we were amazed because this difference is just 0.5 to 1 part per million. So out of that 400, it changed by less than 1, and you could see it in the data. So we were super excited to be able to see this in the data. We were super happy there was a giant El Nino that made these big effects. And another thing that happens with this whole circulation, so I just talked about the ocean, but you can imagine because of the change of winds, the change of temperatures, you often get drought and temperature changes in the tropics. And this is a little illustration of some of the key effects that were seen in the tropics during El Nino. So this region in South America had the driest year it had in 30 years. And Africa was the warmest, and this was also incredibly dry and warm over Indonesia. So if you think about what's going to happen to the plants when it's that warm and that's dry, you can imagine they're going to respond, and it's going to change the carbon cycle. So we have a researcher at the Jet Propulsion Lab that runs a model that simulates how air is moving around, simulates the carbon dioxide interactions of the plants, it simulates another gas that's given off by burning, and she models these things and uses observations and tries to say, well, what did the plants do? Were they doing photosynthesis? Were they dropping their leaves? What happened? And when she did that, she predicted from her model, supported by the data, that you had more carbon dioxide in the atmosphere over each of these continents during the El Nino. So we see El Nino effects in carbon dioxide. And what was really awesome with this work is that she could see that each continent behaved differently. This increase in carbon dioxide was because there was fires over Indonesia. In Africa, it was because there was more rotting of the dead leaves and litter. And in South America, it was because the plants just didn't really grow. So we were very excited because this is the kind of stuff we plan to do with this mission. We wanted to say, why is carbon dioxide changing from year to year? Which part of the world is it happening in? Not just on average, but which part of the world? And you can see we were able to do that because of the big El Nino. These are big changes in carbon. What I didn't show you here was when I say carbon changed by almost 1 gigaton, which is 1 billion tons, you might not know if that's big or small. When the US burning fossil fuel in a single year, we release 1.4 gigatons. So these are numbers that are roughly half of the total fossil fuel emissions of US, but it's happening in 3 different places in the world. So it's a pretty big signal in the whole carbon cycle. And George's question about what's going to happen to our world if we increase carbon dioxide, well, we think this El Nino is a good experiment to help answer that question. Because we saw that it was warmer and drier in these tropical regions, and our expectation is as temperatures increase, it will be warmer and drier in many places of the world. And when we saw warmer, drier conditions, the plants didn't take up as much carbon dioxide, they left it in the atmosphere. So we think this indicates in a warmer, drier world, you'll see more rapid increase in carbon dioxide in the atmosphere. We call this a positive feedback. You put some carbon dioxide in, heat and warm things up, the plants don't work so well, so they leave more carbon dioxide, and it kind of amplifies the response. And since I haven't got my 5-minute warning yet, I'm going to tell you one more thing. So this was super fun for us. People have been working on this project for years. We got in space in 2014, had this El Nino 2015, 2016, and actually learned something about the carbon dioxide cycle of the world. We consider this success in my world. This was awesome. But we don't stop with one success, right? We want to do something more. And in fact, these satellites we put into space have a limited lifetime. We have to, sometimes you build up a set of electronics and pieces that work inside, and you only have one of them, so if something breaks, you're kind of done for. So we're always trying to plan ahead. And we are building a piece of hardware right now to install on the International Space Station. And the idea is this will help us continue our record of carbon dioxide measurements. So I don't know how many of you are space fans, but this is the core of the space station. These are all solar panels. And this thing is like the size of a football field. It's a huge device flying around in space. That's why you can often see it if you go out in a dark night. You can use an app and find out if it's overhead, but it's so big you can often just see it in the sky flying over you. There's a spot here that the Japanese collaborate with the US and they install scientific instruments, so we're building something to install there. And we want to continue this carbon dioxide record. In case OCO2 is not performing, we'll have this additional information. And then there's some special things we'll do about how plants are behaving and what humans are doing. So let me just show you. Okay, this is super fun too for our engineers in the front row here. These are drawings of what the plan is for the hardware we want to build to put on the space station. And this thing goes up in a rocket, a robotic arm comes out and grabs us by the hook. And then this is what they use to plug into the GEM-EF. It's kind of like Legos in space. No humans are touching this thing. Robotic arm grabs it, plugs it in, and off we run. So this is our engineering drawing, and this is a picture from last week. So you can see the resemblance of the things, and we're so excited because this is actually built and being tested right now. So this is how it'll plug into the GEM-EF. This is where the robotic arm grabs it. This is something we use to look at the stars and know where we are. So we have this hardware built. This is the other side of it, a little less exciting. And this is just to give you a sense of the size. This is that box. These are the techs. And it's being lifted on a crane to attach a piece underneath. So this was happening just last week. And I mentioned we want to look at plants and we want to look at what humans are doing. So it's pretty exciting to be on the space station because there's other instruments up on the space station. And in a few weeks, they're going to install a new one that's going to look at evapotranspiration, or how much water do the plants take up? Do they have all the water they need? And then shortly after that, they'll install this one that's looking at how much plant material is there, how much mass is there of the trees. And we're going to go up and look at carbon dioxide, and we can also see a signal about photosynthesis that I didn't talk about today. But you put all those pieces together, how much water stress is there, how much plant material is there, how much carbon dioxide is being removed and released, you can really learn about the cycle of the plants and test out if you understand what's happening. And I'm sorry this graph didn't come out perfectly, but let me explain that a time series of our emissions as humans, and you see it's going up, and what you can't see is that there's actually growing uncertainty. And why is this? Because it used to be that the US and Europe really dominated emissions, but now we have so much growth happening in China and India. They're big contributors. We have megacities developing in Africa, Middle East, and all of those places are contributing, and we don't have inventories or understanding of their emissions that are as good as what we had for the US and Europe. So we know about what the number is, but there's less certainty about it. So we think there's an opportunity to add a little information. If we can measure where the humans are emitting, we might learn more about exactly what the number is. And we tested out some of these ideas. This is OCO2 data as it crosses across Los Angeles. And you can see that where humans are in LA, it tends to be redder and more orange than where the desert numbers are. So we see what the effect of humans are emitting over LA. But we just have this little kind of slice of data through here. And a lot you don't see. So what we want to do with this new instrument on the space station, we have this super cool pointing system on it. It can be very flexible. We're going to do these series of scans. So if we're flying on this blue line, we can look over to LA and do a few scans across the city. And this is a night lights image. So the lights are where the humans are and have lights on. This is the San Gabriel Mountains up in the back. And then we can kind of map over this whole city. And we could do this for like 1,000 cities across the globe and get a lot more information about what's happening in urban areas. So we think that can help reduce uncertainties about what humans are contributing. So I'm going to stop there because I think I've chewed up my allocated time. But we're really excited to be learning more about the carbon cycle. Carbon dioxide in our atmosphere is a big driver of climate change. There's still questions about where in the world the natural system, like the plants and the ocean, are taking it up, what they're going to do in the future. We hope that by understanding a little bit more of the details that will make better predictions. And for me, the whole motivation is we want better policy. We want good plans. We want to make the right decisions, and the more information we have, the better we're going to do that. And exciting for the OCO2 crowd, the big El Nino 2015-2016 really changed some things in the tropics, and we were able to see that with our data and explain what we saw. And we have the support of NASA to add additional measurements for the future. And the really good news for us is that omnibus bill that was signed yesterday actually put language in that said launch OCO3, because in earlier versions of the bills it had said kill OCO3, so we're excited. And I am happy to answer questions and clarify things. Thank you.
Methane is also a very powerful greenhouse gas. A lot of it leaks from 1,000 oil wells in the Los Angeles basin, and from millions of sources of exploration, extraction, distribution. Do you have any devices or plans for devices that can, from space, measure leakage and methane concentrations?
All right, so that's a great question. I can see we have a very informed audience here. So methane is more difficult than carbon dioxide because of all the sources. And we're fortunate that there are some new measurements. One thing we're doing through JPL is flying aircraft with measurement systems that help us map out some sources in small areas. But the Europeans just launched the satellite about a month ago, or two, no, they have data now from November on now, and they see methane with their satellite. They see footprints about 7 kilometer by 7 kilometers. So they will see many of the enhancements of methane due to everything from agriculture, landfills, oil extraction. So I think there's a new data set that will be used to answer some of these questions. It's a regulatory nightmare though, because there's so many different sources of it, but it's the next big challenge after carbon dioxide. All right, you want to come on up?
Yeah, I'll follow up on that same question about methane. Do you have any estimate, do you know the estimates of what percentage of the methane is produced from various sources? In other words, what percentage from livestock, what percentage from fossil fuel production and usage, by that I mean burning, what percentage from plants, et cetera? And do you have any suggestions, this gets into kind of a regulatory matter, how easy or difficult might it be to control these different sources of methane that are out there?
All right, so I'm aware of those numbers, but I don't carry them in my head, unfortunately. But I mean, that would be a great topic for another climate forum to talk about methane. And in my kind of reading in a general sense, I think there's industrial releases could probably be pretty well controlled relative to where we are today, because there is technology, but applying it to all the sources is going to be hard. Landfill captures made an improvement, but there's still room to go. But agriculture is probably going to be one of the harder sources to control of methane. But I'm not an expert in that area, so I can't really probably appropriately answer your questions. Sorry.
How does production of cement increase carbon dioxide, and does macadam blacktop do the same thing?
All right, so yeah, so cement's not something we think about, but so the question was, how does cement production release carbon dioxide, and what about things like asphalt? And so cement, through the process of turning limestone into the material you want, it goes through a furnace and a chemical transformation that releases the carbon. So it's a calcium carbonate is one of the key ingredients. And when you start adding up all the cement production across the world, it's actually a significant contributor. And things like asphalt are not a carbon dioxide release, but they are reliant on fossil fuel and oil extraction. So you're going to take a hit either way. And I think one of the things you'll see in activities around Pasadena is they try to now reuse cement. They grind it up and then put it back into the production that they're doing. So that is one way that we can reduce the cement release. You brought your laptop.
Yeah. Thank you for your presentation. So there are two questions. The first one is about global dimming, which is a concern, especially to me, because ironically, with the release of fossil fuels, there are tiny particles that absorb solar energy. So it actually makes climate change or global warming less. And as we reduce our use of fossil fuels, then there's going to be less global dimming and more solar radiation. So what's that going to do to more climate change and global warming? And the second thing is, do you guys work on like regional climate change, or put this science into regions, because there are people really suffering in areas, that are really hard impacted by local pollution sources?
All right, great question. So this idea of atmospheric dimming, if I understand you right, you're kind of pointing to the fact that we co-emit. When we emit carbon dioxide, there's also other air pollutants, particulates, etc. And so the fact that we've had all these particles in the atmosphere has actually not made us warm up as fast as we might otherwise. And it's a complicated question, because one way we talk about climate change and reducing CO2 emissions is a co-benefit. If we reduce the burning of fossil fuels, we reduce the air pollution, we probably improve the quality of people's lives and your lung systems and everything. So there's a lot of motivation to cut down on the air pollution aspect of it. But if we do that, the warming will increase a little bit. But I think, the way I think about it is that if we can get on a trajectory to reduce the carbon dioxide, we'll have a little bit of a bump up because we reduce pollution or the dimming, and then we'll gain the long-term benefit if we get the CO2 down. So I think the health benefit and the long-term co-benefit of reducing air pollution and CO2 probably win out over the small bump up of heating that we get from removing air pollution. We do some work on regional climate in the groups around JPL, mostly in model development and trying to improve prediction. And some folks are also interested in the intermingling of air pollution and carbon gases. So there's activity, and also at the university, like UCLA has a big activity in that area too. Hey.
So I was excuse me. I was interested in your statement that the variation of uptake of CO2 from the land and the ocean varies quite a bit, 20% versus 80%, you said, in a given year. And I gather your research is focused a lot on the El Nino impact on that, which would sounded like it affected both the ocean and the land uptake. I mean, to me, I would think all the deforestation, you would think that overall the land uptake should be going down, but I don't, I'm curious if there's anything besides El Nino that you understand about what's affecting this variation in land uptake in particular. I know the ocean is very complicated.
Yeah. Well, I mean, in some ways, the ocean's easier, but things with the land, so as you mentioned, the El Nino was a big driver, and it's thought to be one of the big reasons for the variability. And we saw that this year in the tropics. But then you have other things like temperature changes in the more northern regions, say Canada, they know their growing seasons have already shifted. And so the question is, if the growing season shifted, does it become longer? And does that let the land take up more carbon dioxide? That might be one effect that you see. The temperature and precipitation patterns changing is one thing. Like a lot of parts of the world, especially Africa, see more variation between extreme drought and extreme precipitation. And so that's that feedback into the land. Just trying to think of all my land effects. And deforestation has been interesting because there was a global effort to try to create a system that motivated places like Brazil to really address the deforestation. And so we did see less deforestation for some time, although it's not clear if we've studied on that or you continue to see improvement. So that 9% number is kind of an average, and I think it was worse than that. It's gotten a little bit better. And then there's some people will argue that, mineral availability will eventually be limited. If you have enough water and precipitation in some of these places, there's just not enough good minerals in the soil to let the trees even grow further. And nobody knows where that comes in the long-term records or long-term projections of things. So there's still some questions out there. We'll keep talking as long as you guys let us, George.
Thank you so much for your talk. I really appreciated it. I have a question about regional policies and how much effect they may or may not have on global climate change. The Forest Service in California has a policy of doing these huge fuel breaks, and they slash and burn the piles. So my question is, if the Forest Service were to eliminate or reduce the policy of slashing and burning and taking down dead trees, it's a two-part question. Question one, if they left the dead trees standing in places where they aren't going to fall on things, how does that contribute or not contribute to the increase in carbon? The second is, if they stop the burning practices, how does that change things?
Wow, a bunch of deep thinkers here reaching beyond my knowledge. So I'll address this as my sort of citizen scientist perspective, because there were some really interesting statistics this last year about those huge forest fires we had in California and how big the CO2 emissions from those fires were relative to kind of the state budget. And they were big. They were not just on the fringes of things. But I haven't thought that much about forest management policy, other than we know that replanting needs to happen. And I think in California and the whole burning of the forest is this complicated question of forest health. Like, how do you get the healthiest trees? Do you need to clear out this stuff that's been there forever, or let these natural forest fires burn and then it goes through its cycle? And you clearly know way more than I do about that. But all I do know is these fires were big enough, they kind of have to be added in the budget. And if the future holds more fires, that's one of these concerns about these feedbacks of what could happen. And drier, warmer conditions, we'll see more fires and we'll see more carbon released from it. But I don't know how you control that or reduce that, because the way we think about it is kind of driven by temperature and water vapor, rain, rather than Forest Service policies. So I probably don't have an answer, is basically what I'm saying. Hey.
Thank you for a very interesting talk. This question, I guess, might not be right on the footprint of your talk, but it seems like you have the right skill set to maybe take it on.
Okay.
What's drive that up higher. What's the current thinking, and I know this is a classic question that kind of creeps out us environmentally conscious folks. What's the current thinking on sort of direct intervention for remediation, like altering the albedo of the Earth on purpose?
So it's a great question, and we do discuss that amongst ourselves. So the question is, what's the thinking about direct intervention? And there's a conversation happening around the scientific community that if you want to reduce the warming, We talked about how sunlight comes down and gets reflected back in, and when gases trap it, you get a warming. If you just keep that sun from getting down to you, it's another way to keep from getting warm. So people have proposed to put aerosols in the stratosphere. They've proposed to seed clouds down near the ocean surface. They've proposed to put reflective particles in the stratosphere. And these are all ways of reducing the radiation that gets in. And there's a lot of concern about doing something like that because we probably don't understand all the effects of what would happen. But it's a problem because anyone or any country could decide to go down that route and put something up in our atmosphere. So there are scientists that spend a lot of time trying to model these things. And my personal understanding is that we don't understand enough to go and do one of these things, especially stratosphere, because you put something up there, it takes 20 years before it comes back out. We might want to do experiments with seeding clouds over the ocean that make them more reflective, because if you decide you don't like what's happening and turn it off, in 6 months the effects are gone. It may be something the world wants to turn to in 30, 40 years if we can't get our emissions under control, but right now it's a pretty risky proposition. But it should be studied and understood, or we're never going to know what to do about it. I think people need to understand it so we can make a good decision. Got one more, George? All right, last man?
Yes. I don't know, that's asking a lot.
All right, we got to get you on film. Yeah.
Okay, the question has something, you may not have the information, but from my point of view, it seems like what you're doing is crucial. The science is needed. That's maybe the only way we're going to figure our way out of this. And the question I have is funding consistent and increasing, or are the folks that are doing this sort of funding, are they private? Is it the government? Is it, is the money that's needed there?
Yeah. No, that's a great question, and your answer may vary. So I'll speak about my experience here in the U.S., which is clearly different from researchers we know in Europe and Japan and other parts of the world. And we have been fortunate over the last decade to have good support from primarily the Senate and Congress, ensure that NASA's funding has been stable and includes what we need to be able to get this kind of work done. Administrations have varied in their perspective. Obama was very supportive, Trump's not so much, but fortunately Congress is really important in the funding mechanism. So for NASA Earth Science, things have worked out pretty well for us to date. Colleagues who work at other agencies like the Department of Energy, the NOAA organization, and EPA, these groups have been much more under threat with their funding, and they contribute important pieces to the puzzle, like those atmospheric models of what's happening. A lot of Department of Energy and NOAA work contributes to these things. So there certainly are threats to the funding in the U.S., and I think to the policy making, which is the important next step. I can figure this out, but someone's going to decide what to do with it. So to me, getting the right politicians into office, particularly in our Senate, in our Congress, House of Representatives, that's where we can most effectively ensure that we continue to do this work. All right, thank you, George. Thank you, everyone.